Welcome everyone to the last session in track 2. It was probably a really amazing journey all the way down, so we have one last talk. Gartner Hype figured out last year that the big trends in artificial intelligence are four. It's the model-centric, application-centric, data-centric, and human-centric AI. Today we will listen about the data-centric artificial intelligence, especially for SMEs. Our next two guests are, one is Paul Luley, sorry about that, as a research assistant at the ZHAW, at the Zurich University for Applied Science. And he does a lot of groundbreaking research in computer vision, perception, cognition, so an expert in his field. And he will partner together with Schatte from Kistler. He is a business developer, a data scientist expert, a mechanical engineer. So he is the man who knows all about sensing devices, hardware. Welcome on stage, both of you. Warm welcome. Floor is yours.
Yeah, welcome everybody. Today it's my pleasure to present you our joint work where Kistler teamed up with us from the ZHAW and more specifically from the Center for AI to implement a data-centric development process for AI in industry. And more specifically, this process is a plastic injection molding process. And it is my pleasure to explain to you the conceptual and the practical foundation on the software side, whereas afterwards Garrett will take over and will explain to you the business use case at hand. Now, before we dive into the topic, I would like to guide your attention towards the comic shown on the slides, where we can see basically one guy standing on top of a large pile of linear algebra, the machine learning model, and he explains to the guy who provides the data when the one asks what they should do if the machine learning model does not perform well. Well, we just should stir the pile of linear algebra even more. And so he basically does not take into consideration that the data could be furtherly tuned. And this is a common approach and commonly known as model-centric AI, where the task of data preparation and data collection is considered a one-time task. And after this collection and preparation, the machine learning engineer takes over, uses this data to iterate it over the model, but only the model, to improve the model and achieve an accuracy as high as possible. Now, this approach is actually the prevalent approach, and why has it prevailed? Well, never change a winning team. This has led to important advancements in the last 15 years. So the incentive to change from that is very low at the very beginning of it. But at the same time, machine learning engineers are somehow taught to think in this model-centric way because scientific competition is also driven on the performance evaluation of a model on a fixed data set and a fixed data set. And therefore, we are taught to tune the model's architecture, to tune the hyperparameters, to modify the loss function, and to account for high bias or high variance, all under the assumption that the data set is clean and fixed. Because these techniques that we are taught work best when the data set is clean, but it can happen, sometimes it happens, that even if the machine learning engineer applies all of these techniques perfectly, that we still cannot achieve the accuracy we want to achieve. And this might, because the error does not necessarily lay in the model, but it also may lay in the data. And the model-centric approach does not account for errors in the data. Therefore, it does not account for inaccuracies in the data, for inconsistent labeling, for missing labels, for wrongly labeled samples, and therefore a prominent example is the following, that back in 2021, Northcutt et al. were able to show that Even well-known and heavily used datasets like MNIST or ImageNet, after years of usage, still contain errors. And if this is the case for even these artificially, or more or less artificially created datasets used for scientific competition and scientific research, then this can even hold more true for real-life datasets. And besides that, the model-centric approach also induces some bias towards the type of company which is able to apply AI. Because the company which applies machine learning must be able to handle large data sets. They must possess the necessary computing capacities, and they also have to have the needed machine learning engineering expertise. So a lot of large consumer internet companies fulfill these requirements, but at the same time, a lot of companies are basically excluded from the use of AI, since not every company, and in our context, an industrial company, which can be considered a small and medium-sized enterprise, does not necessarily fulfill these requirements. And therefore, if we want to really unleash the potential of AI and to some degree democratize it, to make it accessible for even smaller companies, we must reduce and lower these requirements. And therefore, we must, our machine learning model, be able to run on smaller data sets, and therefore we reduce inherently the hardware requirements. But what small and medium-sized enterprises can bring to the table in that discussion is their domain knowledge. So we should use their domain knowledge to make our data set as good as possible, although it is not a big data set. And these requirements actually, or these goals we have, actually correlate nicely with the data-centric AI approach. And this is why we decided to choose a data-centric AI approach for our use case at hand. And to let you leave the room after the presentation with a clear idea in the mind what data-centric AI is and what it tries to achieve, I want to give you the definition at hand. At the same time, I want to give you the properties at hand, and I want to show you also how we did it, so how it can be achieved, what data-centric AI tries to achieve, and what role MLOps can play in this game. So data-centric AI, the term itself, was coined by Andrew Ng in March 2021. And from there on, he hosted also a workshop at NeurIPS, which led to an exponential increase in the number of publications of data-centric AI. It's also led to research institutes like us, or the ones from ETH or Fraunhofer, to start thinking in a data-centric mindset. At the same time, nowadays, there's also a course from MIT, which introduces data-centric AI to the students. And last but not least, there are also data-centric companies that profit from this new hype. Now, regarding the definition, data-centric AI can be defined as the discipline of systematically engineering the data used to build an AI system. And I want to put the emphasis on systematically engineering the data, because we want to create a system, in some sense, that helps us to engineer the data. And what does this mean with respect to the previously shown model-centric AI approach? Whereas in the model-centric AI approach, the model was only iterated over and the data was kept fixed. Now, in the data-centric approach, we include the data also in our development iteration, which allows us to iteratively improve the data quality under the assumption that we have a reasonably well-working model. So the graphic is a little bit misleading. We don't have to completely avoid model development, but we should have a reasonably good working model on which we can apply data-centric AI. Otherwise, we would just apply the data iteration on random matrices. That wouldn't make any sense. Now, what are we trying to achieve? What are the properties of a data-centric approach? We typically want to achieve consistent labels. Where, if you remember one of the previous slides where I showed you the faulty ImageNet or MNIST, they had wrong labels. So we want to make up for these wrong labels. This results in a data set of higher quality, and ideally we end up with a more representative data set, which covers all the distributions we have in our data. And since we can also apply this circle and this iteration over the data during training and also after the training and after deployment, this procedure allows us to detect a concept on data drift very early. Now, these things we want to achieve with data-centric AI, they nicely correlate with the goals we had in mind to make AI accessible even for small companies whose core competence is not necessarily computer science. Data-centric AI allows us to work with smaller data sets to therefore reduce the hardware requirements, and I want to show you in the next slides how we can actually encode the domain knowledge to make it useful in the data-centric AI approach. Regarding the techniques we have at hand to engineer the data, because remember, in the definition it says systematically engineering the data. The techniques we have at hand to engineer the data are basically the same we know from the model-centric approach, but this time they are applied in an iterative manner. So those are labeling, cleaning, augmentation, reduction, and collection, all with the goal in mind to enhance the data quality. And now you may ask yourself, okay, you know about the definition, what's the goal of data-centric AI? How do we actually achieve data-centric AI? And therefore, we thought about the following process. We met in a workshop where we aligned on two distinct roles in our business process, so to say. We aligned on a domain expert who does not necessarily has to be a computer scientist or a guy who works regularly with code. He can also be the operator in our industrial context of the machine, for example. But his roles and his tasks are to provide the data and provide the labels. And the task of the machine learning engineer are then to implement and to develop a machine learning model, evaluate the performance of this machine learning model, and then actually perform an error analysis. That means to determine whether the error lies in the model or lies in the data. And when it is caused by the data, the bad performance of our machine learning model, then these samples, they have to be identified and have to be forwarded back to our domain expert with the request to look into the data a little more and to actually determine if it is correctly labeled, if it is actually high quality data. And the outcome of our process is naturally a working machine learning model. Now the tools that each of these entities has at his hands is, remember, the domain expert has to provide the data and label the data. Therefore, and since this guy is not necessarily a computer scientist, we thought of some frameworks which help him to ease in the work. So therefore, we thought of some tool to store naturally the data after he does his experiments and after he operates the actual machine. But at the same time, since he also has to create the labels, we want to equip him with some framework which allows him to label the data easily without going into the code or going into CSV files, but actually make this process easier. And for the machine learning engineer, his task is to provide a machine learning model. Therefore, he uses his typical IDEs to develop a machine learning model. But this time, we have two crucial additional parts. So since we, in the data-centric approach, also iterated over the data, it is of utter importance that we track the changes we do on the data. Therefore, we thought of a framework which allows us to not only version the model changes, but also version the changes we do on the data. And since we want to inspect the data and want to inspect where the errors lie, we need some tool for error analysis, which allows us to make this conveniently. And since this is a workflow, I want to give you a glimpse of how we implement it and what tools do we use for this. So to orchestrate this complete workflow, we use Airflow, which allows us to model this workflow as a directed acyclic graph, where each node depicts a task you can see from the previous slide. For example, the data collection, it triggers automatically the data curation, and from there on, automatically the model is built from our version control and is applied on the new data. So to automate this process, Airflow allows this. To actually look into the performance of our model, we use MLflow, which is a tool which also allows us to look into the separate evaluation metrics. Like I said, we have to keep track of the changes we do to the data. There are also different tools available, and we decided to go with DVC, which is built on top of Git, so we know about the typical Git commands, and we can conveniently use them for the changes we do to the data. And last but not least, we also have to account for the error analysis on the machine learning engineer side. So therefore, we thought about error analysis, which is a tool which allows us to display the data as a binary tree, where each edge basically depicts a filter on the data. And whenever we encounter that the data is actually the root cause for malfunctioning a model, then we are able to track this specific subset of the data down with our binary tree, because we can go down the binary tree and look for the feature and the thresholds each feature has in terms of this subset of the data. And now I'll happily hand over to my colleague from Kistler, Gerrit, who will explain to you why on the on the data labeling side, we have to look for a framework which allows us to conveniently label time series data.
Good, thank you, Paul. So let's have a look at the application itself. So I'll just, this is a video showing how injection molding processes work. So you have molten plastic, which gets injected into a mold where it cools down and becomes hard, and it is ejected from the mold. Very easy, but actually quite a complicated process. The characteristics of such a process can be very well encoded in the so-called pressure curve. If you have a sensor in the cavity and you monitor the pressure inside the cavity over time, this is like a fingerprint of the part which will be injected. So it tells you, you can see if it's going to be a good part or a bad part, and even much more in some cases. The problem we're trying to solve with AI, which and where, let's say, the model-centric approach alone stands in the way of solving it all the way, is that at the moment experts have to label the curves as good or bad, or have to define the shape of the curve, which is going to be a good part and which is going to be a bad part. So actually a very nice problem statement, but there's a but, and this is where this approach comes in. I mean, if we look what will happen in the future, I mean, you can imagine shop floors as large as this room or even larger, full of injection molding machines and very limited personnel trying to manage that all of these processes are running and that good parts are being produced all the time and that there are no anomalies. In the future, we will have even less personnel. So it is our task to somehow facilitate a higher automation of this process. And this means initially trying to reduce the amount of expert inputs needed for stabilizing a process, or even for filtering the parts or solving errors. So this is why we want to explore the use of AI for this. But like Philip mentioned, there are a couple of issues which stand in the way of just moving forward and doing it. So historically, as displayed here a little bit, we have multiple applicants of this pressure collection technology, and then they store the data in their own format, let's say, maybe even different standards of technology, as these systems have been around for quite some time. Some system 10 years ago may store the data differently than the system sold 5 years ago, and there are different amounts of data. It's quite heterogeneous. So this is what this is supposed to say. We have different heterogeneous data, and with those we want to somehow train a model or groups of models that can represent this process well enough in order to take over this task scalably. And so this is where this new approach comes in as compared to the model-centric one, where we can actually, as we go through this project, learn what maybe the ideal way of conditioning and transferring the data is to the model, rather than the way it is now, in order to facilitate, let's say, this scalable and deployable final model then. So this is why we need this process. So it's a chain of problems which we have here. And yeah, I'm very happy to actually have learned about data-centric development. I myself was a model-centered guy through my education. It was hammered into my brain, the model-centered approach, and I'm very happy that my horizon was broadened here by working together with you guys from ZAW. So thank you for that as well. So, and with that, I hand back to you.
Yes, just the very last slide. I want to give you some takeaway messages. So please, I hope we were able to convince you that the actual looking into the data during the development process makes actual sense, and that this process should be integrated in your development process of a machine learning model. But at the same time, we don't want to demonize the model-centric approach. It's kind of a shift, not a turnaround. We still need the skills we need to model, to develop a nice working machine learning model. But yeah, whenever we cannot explain why we are not performing as well as we should, maybe it's a good idea to look into the data as well. And of course, the tools I presented to you are to some degree tailored towards our use case. So I think they are in some sense abstractable and also maybe one-to-one usable for your use case, but they are not all tools that are available, so choose your tools appropriately to your use case. And yeah, with that, I'm happy to answer any questions. Thank you very much.
Thank you very much, Paul, Gerrit. Maybe come here a little bit into the front of the stage, not hiding over there for the quick questions. It's the last session. I hope there is some interest from the audience. There is one over there. There's already this. Oh, there.
Okay, thank you very much. So in this iterative cycle between the domain expert and the ML engineer, when you flag a sample as erroneous, don't you think this might be a bit suggestive? And because sometimes the labels are not, let's think about medical imaging, right? And you use it to do a diagnosis, and then maybe the first hunch is actually the correct one. But if you flag it as erroneous based on your metrics, and you send it back, then the domain expert will actively look for mistakes, and that way you could maybe introduce, unwillingly introduce a bias. How would you account for that?
Yeah, so I expect the domain expert to know his stuff way better than a machine learning engineer. So this might be a case where the iterative process just goes through and nothing changes on the data. But yeah, of course, this might introduce some bias, and the domain expert may think, well, I'm wrong, and but then he has to ask his colleagues or to somehow verify that his opinion and actually the label is correct, which is which is not bad, I think. Well, this just proves one more that the data is correct, which is totally fine, which is not a waste of time, in my opinion. But yeah, you're right.
So you suggest like implementing a protocol or standard procedure?
Exactly, yeah. So that's what we, that's what I would suggest in that sense. That in that case, we know how to proceed and we know how to work further.
Thank you.
In reality, if you have now, you start your problem, you have some data, you optimize, you start to train the first model, your concept basically says you freeze at some stage the model and work on the data. How does it work in reality? So when do you think you have reached the stage where you say, okay, let's freeze the model and work on the data? Is this like a clear boundary, or?
This is also subjective and also dependent on the use case, I think. Whenever we achieve the accuracy we want to achieve with our early model, which might not be as high as a full-fledged model, which is the result of several model-centric iterations. But if we have a good benchmark, and we agree that with the domain expert, for example, that our benchmark is reasonably good, then from there on we could, for example, start with the true and pure data-centric approach and iterate only over the data.
Usually would success one by one, not both together.
Sorry?
One by one, so for either the model or the data, or this is like one cycle altogether?
I would propose a one by one. Just first get a reasonably well model, then try to improve the data. As soon as this is reasonably done, then maybe looking into the model again, and so forth and so on. So we can improve on both sides step by step.
I would say we have different approaches which we explore. They all have their own kind of freeze state they are supposed to converge to. But that doesn't mean that, we can add additional approaches. It only means that maybe a model in certain type of architecture, certain approach, then kind of converges, let's say, to what it will be. But then we can leave it as that and take a new approach.
One last question with a short answer.
If you have a lot of data to label, let's say, do you apply some sort of active learning metrics things to choose the labels?
Sorry?
Like, let's say there's too many samples to label for the domain expert because it takes a while. There's like, how do you choose which samples to show, or don't you have this problem?
So since we are working in a very low data regime, so to say, so at the moment we didn't encounter this problem. But whenever it comes to data relabeling, active learning is a valid approach. So this is actually what I meant when I was talking about the techniques we have at hand to engineer the data. So then, of course, data relabeling can also include active learning.
Thank you very much. Paul, here a bottle with your name on it, the data bottle anniversary body. Big applause for the last two guests here on stage.